We are happy to have our old friend LianTao Wang from University of Chicago to tell us the signals of new dynamics during the inflation.
Should I start?
Yes.
Yes.
Okay. Thanks for the invitation. So my topic today is about using inflation as a stage for seeing new dynamics. So there are two aspects of it. One is that inflation corresponding to some very typically corresponding to some pretty high energy scale. The temperature during the inflation can be as high as 10 to the 13 GeV. And therefore, there's enough energy in principle to produce very heavy particles beyond the reach of a terrestrial experiment. At the same time, Inflaton can also travel a large distance in field space. And so if there's any spectator sector that couples to the Inflaton, you can imagine that easily you can trigger some dramatic changes in that in the dynamics of the spectator sector. Okay, so I'll give you some example in each of these cases. So, yeah, so this is the basic content of my talk, and I'll talk about two of those examples. I think if I don't have enough time, I may talk about the second one. Maybe may not in full detail, but I will try to give you a flavor of it as well. Okay, so let me begin with the signal production, signal particle production. So this is sometimes known as the cosmological collider physics. So the basic idea is that you have somehow I lost my okay. So you start out with some particle getting produced, and somehow I don't see my point. Would you mind if I do it like this? This way you can see the pointer.
That's okay.
Yeah. Okay. So a particle is produced, then sort of in this picture the particle is produced, then it propagates, and this theta is supposed to be the Inflaton mode. They interact with the Inflaton mode both at the two very different time scales, measured by the inverse of the momentum. Yeah, so this is a typical limit. People consider this kind of 3-point function where two of the momentum is much bigger than the other one. So these two are corresponding to a short time scale. This one, k long, is corresponding to a long time scale. So the signal, the wave function, the time of the propagation from this picture and work it out to be, since the ratio of the momentum is during inflation is exponential of the time. So the time of propagation is a log of this ratio and divided by 1 divided by h. Okay, so that's the time of propagation. So the wave function of a propagating particle is some sinusoidal function of m times t, and plug in this t here. You see that we'll get this kind of oscillatory signal that's oscillation in log of the momentum ratio. So this is the analogous signal of a resonance spectrum, if you want, at the usual colliders. In this case, we are looking for a signal oscillating in the log of the momentum ratio. Okay. And so let's look into a little bit into more detail about the signal. And so this is schematically what the signal look like. So this is the 3-point function, right? This is how it's normalized. And it can have this basically 3 pieces. And this is So this is some Legendre polynomial. S is the spin of the particle that's getting produced. Okay, so but let's focus on the first two factors here. The first factor is the typical Boltzmann suppression. So nu is defined in this way, and it's the Boltzmann suppression factor. When so if the particle you wanted to produce is much heavier than Hubble, and then it's you have enough energy to produce them. And then this is the oscillatory piece, especially the imaginary part here. That's the oscillatory piece. You see that if the particle mass is too small,
Turn off your sound.
I can't.
is that okay?
Sorry, we are getting a speaker.
Skype or Zoom doesn't let me do that. So
You just turn off your speaker and turn off your.
no, I can't. Can you turn off yours?
Should I continue or should I wait?
Go ahead.
Okay, so if the mass is too small, and this you also lose the oscillatory signal. So this is the special part of this cosmological collider is that mass has to appear in a mass window around the edge. Okay, if the mass is too small, you're still going to generate a non-Gaussian signal, but it's not going to be oscillatory. Okay, but if you're going up purely the resonance production, the signal, then the mass needs to appear in the window. So yes,
Go ahead.
Hi, can you hear me?
yeah.
Okay, I'll ask a question. So why oscillation is so important?
Well, so it's important because it tells you there's a particle being produced. It's like in usual collider physics, right? You wanted to see some kind of resonance. So this is similar to the resonance signal. In principle, you can infer the existence of a particle by other means as well, but this is a direct signal.
Okay, thank you.
Okay. And yeah, so if you just want to have some idea about what kind of particles this might be produced, right? Let's just have some example. Imagine the inflation scale is 10 to the 16, and h will be 10 to the 13, right? So imagine that this can, for example, in a Sway framework, this can be the gut scale or string scale, where the superpartners in this case will have a mass on the order of h, because the de Sitter space itself is SUSY. So that can be one of those signals that with mass appearing this window, or maybe there's some strong dynamics at this high scale. In that case, perhaps the Goldstones will be from the strong dynamics can be naturally several order magnitude below the strong dynamics scale, and it will appear in this window. So this is just a couple examples. For example, the kind of particle may be able to produce with in this mass window. Okay, so there have been quite a number of works in cosmological collider physics, both on the formal aspects, how to compute this kind of amplitude in some special limit, and also in its phenomenological applications. So here I'm going to focus on one aspect, just like in usual particle colliders. We wanted to at least have some idea about what size of couplings, what kind of couplings, what size of couplings we can probe with this kind of signals. I wanted to ask the same question for the cosmological collider. Okay, so let's look into a little bit deeper, closer with the cosmological collider signal. So this is how usually the 3-point function is normalized. p theta here is the 2-point function, and that's been already observed to be 2 times 10 to the minus 9. It's a small number. And again, I'm thinking about just usual slow roll single field inflation, right? In that case, a single rolling field has a background value about 60 times h. And this S function is usually called a non-Gaussian entity, f measured by some number called FNL. Right, so what this is where the actual interactions enter. Right, so typically it's normalized. There's some normalization factor, but beyond that, there's just the usual interactions that we are familiar with. The interactions can include couplings, loops, and the propagators, and so on. Okay, and just for give you a sense of numbers. So Planck has measured this number down to the size of a few. Future large-scale structure surveys can push this number further down, and ultimately 1 centimeter measurements is supposed to push this down to 10 to the minus 2. So this is the kind of size, 10 to the minus 2, if you want, is the ultimate limit that we can think about the size of signal. Okay, so otherwise, if its signal size is below that, there's no hope. Okay? Well, when the signal size is above that, if it's clear enough, we have some hope of seeing it. Okay, so let's start with the seemingly most obvious couplings, the directly couple Inflaton to some new physics. Let's call it a sigma is a star. And these are a few interactions. Actually, are not the most. Maybe it's not the most theoretically well motivated coupling, because we all wanted to Inflaton to have some of approximate shift symmetry. But nevertheless, these are perhaps the couplings that you think about it first. So let's just try this kind of couplings. And a major effect of this kind of coupling is that a non-zero value of Inflaton field will actually give you a mass for the particle that you wanted to produce. Okay, and now remember that we really wanted the mass of the new particles to be appearing in some mass window, and if I without any fine tuning, we need this contribution to be less than h squared. Okay, so this sets a limit about how big this lambda can be. Yeah, for the similar reason, you can also set a limit about on this mu parameter. And now let's just example assemble a 3-point function. It's just very similar to drawing a Fermion diagram. And what's important for the estimator is just that there's a loop factor, there's some couplings that I'm going to use, and so on. Okay, there is the coupling showing up, but again, from the requirement I mentioned on the previous slide, this coupling needs to be less than this. So this is the signal size that I'm estimating. Now the question is, what is phi naught? Okay, so what is the typical value of field value of Inflaton field? So, okay, for this, let's remember that Inflaton field usually it actually evolves, depends on the number of e-folding. Okay, so it will be, and then this is approximately this. This is the field value, excursion value, and even if for number of e-folding, not even order 10, but order 1, you see that this is a large. I have to, the Inflaton has to go through a pretty sort of significant field value excursion. Okay. And so if I use this field excursion as a estimate of the field value, I get this estimate of h over phi naught. Okay, and if you go plug back into this tells me that the size of the signal is this. Remember, this is a very small number, so this signal is not observable. Okay, what have we learned here? So to summarize what to learn here is sizable coupling to the inflaton, direct coupling of this can generate a mass correction to the matter field, any matter field you wanted to produce. So to see this oscillatory signal, we want to require this not to be this correction not to make this field too heavy, and this in turn requires the coupling to be tiny, and this leads to a very small signal. Okay. By the way, we also cannot really avoid this by fine tuning, because what's really going on is Inflaton actually traverse a large distance in the field space. You can at the most fine tune for one of the field values. You can not tune for the full range. Okay, so next let's start to consider more reasonable couplings. So that's derivative coupling. So this is a consequence of, this is very well motivated, right? Because we do expect Inflaton to have some approximate shift symmetry. And it turns out also this is also favored for giving a sizable signal. Okay, so let's begin with the dimension 5. And so at dimension 5, there's this kind of coupling. So this is a fermion current, and this is the F by F type of coupling. So we can follow through is a estimate like I just did earlier, and this is the simple estimate. Okay, so and look, there's a 1/4 on this small number, so it's already much better than the UV. And I think a lot has to do with that. If you Inflaton background for this kind of coupling is phi dot. Phi dot, instead of going through a very big range, is approximately a constant during the inflation.
Okay. How big did you assume lambda was?
Oh, yeah. So lambda. So for phi dot over lambda to be a good effective field theory expansion, phi dot the lambda, the smallest the lambda can be is the square root of phi dot. Okay, so I was using that. Okay, so the optimal case, the small lambda. Okay, it's still where the derivative expansion is valid.
What is that in TeV?
What is that in TeV? Okay,
TeV
phi
or
dot is
EV 10 to the minus 30 EV. What? How big?
So phi dot is 30 times, so 60 times h, depending on what you want h to be. Okay, so if h is 10 to the 13 GeV, and this is almost 10 to the 15 GeV, phi dot square. Yeah. So, yes. And at the same time, this is not the end of the story. There is another, turns out there's a further enhancement in addition to this, because of this kind of couplings. This is the coupling come from particle production. Okay, so due to the modification of those couplings to the dispersion relation, so the particle production actually is proportional to omega dot. This is sometimes known as the adiabaticity parameters, omega dot or omega square. And so the modified relation inflationary background from those kind of coupling is of this kind of form. Okay, so if you have a modification of dispersion relation of a coupling in this form, okay, there's something linearly proportional to K, and with this parameter I call mu, and you see that there is an enhancement come to this parameter, which is proportional to mu. Okay. So if the mu is sizable, I will have a large enhancement. Okay, so it's pretty, you can pretty, in general, you can argue that the word, what kind of coupling give you this kind of dispersion relation, right? So basically it has a factor, one factor of momentum. And sorry, to preserve rotation invariance, this vector has to be dotted into another vector. Okay, so the other vector that can only be there are the from a particle physics point of view is the spins. Okay, so therefore we can only have, for example, the coupling to the fermion current, the coupling to the vector current to the spin one particles. Okay, and in both of cases, those W parameter is phi dot O lambda. Okay, that's the W parameter. Okay, so again, if I take the optimal case, the lambda is square root of phi dot, and this is basically square root of phi dot. Okay, 60 times h. That's the largest value for this new parameter. Okay, now I'm just going to quickly estimate a signal from the fermion current. So this is the coupling that couples to a fermion current, and that term does two things. One is that give you this new parameter, the phi d phi on its background value, give you the new parameter. The second is also generates a coupling of the inflaton fluctuation to the fermions that you use to draw basically this diagram. Okay, so that's the coupling there, and we can just through with our estimate and see that in fermion case, this is interesting. The end is quite interesting. So there is a term like this that would have a Boltzmann suppression if there's not a mu parameter, right? And there is also a enhancement due to particle production due to the mu parameter. And in the limit when the mu is much bigger than h, and you see that we can have a form like this. This is even for mass is greater than h. This is not a suppression, not necessarily a suppression. Okay? It doesn't go like equally m over h basically. Okay. So what's happening here is that the enhancement coming from particle production cancels the suppression coming from the Boltzmann factor. Okay. So this is just
LianTao, is this mu chemical potential?
I don't like to call it chemical potential.
Okay.
But yes, so collaborator likes the chemical potential. But
okay.
It's not the kind of chemical potential that distinguish particle versus antiparticle. So it's the kind of chemical potential that changes the dispersion relation.
Okay, got it.
I don't know how should yeah. Anyway. Okay, so then this is not that important. It's just try to estimate the phase space integral in a very crude way, and get to the end result. Okay. So yeah. So but just in general, we can the cosmological collector signal can be written in this form. There is a piece that's analytic in terms of K1 over K3 ratio. Okay, and then there's a piece that's not analytic. Okay, there's a sinusoidal piece of it, and both these numbers N and L are depends on the model, right? So there's a table depends on the spin of the particle and the mass and so on. You have various different power dependence. So these are the Boltzmann suppression in the case when the mass is large. So in this table, we use the unit of h equals to 1. Okay, so yeah, so these are the Boltzmann factors. And in the case of fermions, there's a large chemical potential, and there is this enhancement factor as well. Okay, there's this enhancement factor. So in this case, it's conducive to give a sizable signal. Yeah. So this is just several different models. So this is in this triangle. This is the fermion model. The particle running the loop fermions, and in this case, this frequency parameter is defined like this, and yeah, so this occupy this region for fermions. So we scan the lambda and so on. Okay, you can scan that the cutoff scale lambda, and this is a different model, which is vector. So it has a different dependence of on the S and the chemical potential, and it occupies some place in the middle. Okay, so this is another. These gray lines are another model, which is coming from a dimension 6 operator, which I don't want to discuss that much further. And they could give you an interesting signal, but it doesn't need to have some coupling needs to be special. And in this case, as we argue, there's not this mu type of enhancement because it's a scalar. It does not modify the dispersion relation in an interesting way. But you see that this is also, these are vaguely, roughly what the various future probes can measure of this NL parameter. You see that at least in this region, they can be there's a good potential that those things can be measured.
What's your unit of frequency?
Sorry?
The unit of frequency is what is the unit?
You mean the uncertainty? I couldn't hear the question very well. So the uncertainty?
What's
your
your
horizontal axis? It's a frequency, right? What's the unit?
Oh, frequency. The unit is this is a dimensionless ratio.
Mm. Okay.
Yeah.
Just this number. Okay, this square.
It's just these.
Okay. Okay.
Yeah. So more recently we did so far the loop integral, the result I show you are just based on some simple estimate of the loop integral, these loops, although these are one loop amplitude, it turns out to be very difficult to calculate. Okay, so it's much harder than the one loop amplitude in flat space. Okay, so it's amazingly more difficult. Okay, so anyways, but I think so far the only tool that we have to actually do this is a brute force numerical evaluation. And so this is a recent work we did. This is the gauge boson loop, and so because we did it the full calculation, so you get a full dependence on this ratio and without any sort of approximation. And this is the full signal. These are the contribution for various polarizations. And but on top of this, there is a wiggle signal. Okay, this is the oscillatory signal. Okay? So it's a if you treat the full non-Gaussianity as a background, these are the signal. Okay, it's a smaller than by maybe 2 order magnitude. It will take some teasing out to template to tease them out. And just how well our previous analytical estimate, very crude, is. So you can make the estimate I just did a little bit better by expanding propagators and so on. Okay, so this is the value. So these are the actual analytical calculation, and this is the gray line are the ones that if you use a semi-analytic approximation to estimate it, and you see that the amplitude more or less agree. Okay, so the estimate didn't get undertaken too wrong. And the oscillation pattern also more or less agrees when you are in a fairly good squeeze limit. So K1 over K3 is greater than 20. When you below that, the frequency starts to shift from your shift a little bit from your naive estimate. Okay, so this could be the fact that the expansion we did in analytical estimation does break down when you go a little bit away from the squeeze limit and so on. Okay, so that's something in the future to really understand better what exactly is the analytical estimation miss. Okay. So this is basically the first topic I wanted to talk about. Next, I wanted to move on to the second topic, which is suppose the inflaton couples to a spectator sector, and it may trigger some drama in the spectator sector. In particular, I wanted to consider the possibility of a first order phase transition triggered by the rolling inflaton. Okay, just to recap. So the basic motivation is that the inflaton traverse a large distance during the inflation. So this is the basic formula. If you in a traditional slow roll inflation, right? So scale slow roll inflation. So this is not too small, and so even just for one inflaton would traverse a big distance. Okay, even if we restrict ourselves to the case where it doesn't go over and Planck, this is still a large distance. So the question is there any observable effect coming from this? So for this, we can consider following scenario. Okay, so we have an inflation factor. It's the very traditional inflaton sector as a single field throw, has some approximate shift symmetry, and we have a spectator sector. The spectator has less energy, so it does not change the inflation dynamics significantly, and at the same time, we can certainly think about they can have some coupling between each other. So, I don't know, just like the string theory moduli field, for example, they even though they can be candidate for inflaton, they can also have and Planck suppressed couplings to spectator fields. That's I think that's very common phenomenon. So generically, for example, we can write the Lagrangian in the spectator sector can be written as something, any coupling, any term in the spectator sector can be multiplied by some function of inflaton divided by some high scale, such as Planck scale. Right. So this is just a generic function of this ratio, and this also goes along the philosophy of the parameters in the field theory is determined by some modular field in a more fundamental theory, for example. Yeah. So, but if taking this framework, it's very plausible that the field excursion and then field excursion of inflaton actually change the mass and couplings, everything in the spectator sector. So this really leads to interesting dynamics in the spectator sector. Okay, so just a toy model, we can write something like this. I'm missing a sigma square here. Okay, so this is the mass term. There's some, yeah. So in general, I can just have a potential like this, and yeah. So the mu effective is its own mass plus there's coupling to the inflaton. Let's just simplify the case to consider inflaton coupling only change the mass of the spectator sector. Okay, so and this number can be much smaller than 1. Okay, so because this can be some high scale. And so if, for example, if you take lambda equals -1, then the rolling of inflaton can change the mass square, and it can go from this solid curve to this dashed curve, for example. And this is the point where you are actually going to have a first order phase transition. This can certainly trigger a first order phase transition. Okay. And so for phase transition is phase transition is a first order, you know, and we also require spectator does not dominate energy. This leads to this kind of requirement. Basically, just a typical energy scale in the spectator sector to be bigger than h to the fourth, but this is also much less than the total energy in the Inflaton potential. Okay, and so in reality, we actually we estimated what kind of a parameter space this will be a first order phase transition, and so on. We verified it with Cosmo transition, and so on. So that's consistent with our estimate. And the basic picture here is that the size of the bubble. So first order phase transition proceed with bubble nucleation. The size of the bubble is typically much smaller than the size of a Hubble. So typically, like this is a 1/10 or 1/20 of the Hubble. So there are many bubbles within the same Hubble volume. Okay, and in that case, the bubble collision is going to give you the gravitational wave, and time duration of that bubble collision can be estimated by the size of the bubbles. Basically, that's a simple estimate. Like how long the collision will last is roughly the size of the bubbles. And but because this is much smaller than Hubble size, and this source of a gravitational wave can be thought about as an instantaneous source. Okay, so it only lasts, the source itself only lasts a small fraction of Hubble, basically. Okay, so yeah, so this is basically the picture, and so this tau star is the time when the phase transition happens, and the delta tau is when the time duration or the source lasts. Basically, the time duration of the bubble collision. And this is what I said is also similar on the same order as the size of those bubbles. Okay, so now the gravitational wave mode is going to be generated, and exactly what those gravitational modes look like depends on whether their wavelength is bigger than the size of the bubble, or smaller than the size of the bubble, or whether their wavelength is bigger than the co-moving bubble size. Okay, so these are the three qualitatively different scenarios. Okay, for three different frequency of the gravitational modes. Okay, so in this intermediate scenario, where the wavelength of the gravitational mode is bigger than the is bigger than the sorry, is bigger than the size of the bubble, but it's less than Hubble. What's going to happen is that the gravitational wave is going to be generated, and it's going to oscillate. Okay, and before it exits the horizon, okay, oscillate. But at the time when it's exit the horizon, the amplitude of the gravitational wave will be frozen. Okay, until it re-enters the horizon, and it starts to oscillate again. Okay, so this is basically the picture in this intermediate region. Okay, so for different wavelengths, it's going to also start at the same time and start to oscillate. And but because it has a different wavelength, the amplitude of the other the amplitude will be different than the first one, right? So in general, in this region, you will have a amplitude of gravitational wave that's oscillate in K. Okay, so different K corresponding to different different amplitude of the gravitational wave. Yeah, so this is just another picture of that. Now for the wavelength of the gravitational much is smaller than the typical size of the Hubble. In that case, the gravitational wave signal still oscillates, but we cannot really treat the source as instantaneous anymore. It's the time duration of the source actually matters. The starting time of the source actually matters. So they will smear out the signal. So here we don't really have any, we don't expect any oscillation signal anymore. Okay, for the UV part. Okay. Now if the gravitational wave signal when it's generated, its size is already bigger than the horizon, then it doesn't really oscillate. Okay, it's just some static thing, and it does not evolve until it coming back to the horizon, and it starts to oscillate again. Okay, so there are these three regions that are very different. So this is just a recap. So this is the IR region, this is the intermediate region, this is the UV part. Okay. And this is what the signal look like. So this is the intermediate part that's oscillates, right? So it's a set when the frequency is when the wavelength of the gravitational wave signal is bigger than the typical size of the bubble, and smaller than the Hubble. In the intermediate region, you will see oscillatory signal, and in the UV part, the signal tends to begin to be washed out, and right. So and in this part, it does not have any oscillation signal to begin with. Okay, so this is oscillatory part, and there's some smearing factor here, and then there is also something that depends on the evolution of the gravitational wave signal, right? So before it exits the horizon, which is encapsulated in this G factor, but also the so this G factor here capture the effect of the evolution of gravitational signal before it exits the horizon, and this factor capture the evolution of the universe after gravitational wave re-enter the horizon. Okay, so therefore the alternative signals, so this picture I think is more or less drawn based on the standard picture where you have a quasi-de Sitter inflation, and then immediately reheat back to a radiation-dominated universe. Okay, so then you have some signal looks like this, and but for a different alternative scenario of evolution, you will see a different. You should expect to see something different. Okay, so we can try some alternative scenarios. So this is again for quasi-de Sitter, for example, this is the scale factor, but one can also try some different inflationary scenarios, such as this so-called power law inflation. Okay, so basically the scale factor goes like t to the p, and the p to the infinity sort of is getting closer to the quasi-de Sitter's case. And one can also try different scenarios after inflation, whether you have matter domination, or whether you have radiation domination, or you have something else first, and then transition into to radiation domination, for example. Okay, so and all of this give you a somewhat different evolution of background field. Will affect the shape of the gravitational wave signal. Yeah, so this is how they depends on different scenarios. So So this is for example, again, we can divide them into 3 parts: the UV part, intermediate, and IR. And for the de Sitter, for example, this is the de Sitter case where you actually immediately get into a radiation-dominated universe, and then you get a k to the minus 5 dependence for the UV part. That's this part. But if you, instead of getting into a radiation domination, but you get into a matter domination first, okay, then the dependence on K will be different. It's K to the minus 7. Okay, so for general TLP inflation, this order can also be different. Similarly, the intermediate part, the dependence on the slope of the sorry, different scenarios after reheating also changes the slope of this part. Okay, and yeah, for the infrared part, it does not depend on the inflationary period evolution, which is expected because the mode in the infrared part are already outside the horizon. They are not evolving during the inflation during the inflation. So they are, there's no difference. And on the other hand, the shape still depends on whether when they re-enter the horizon, whether it's radiation domination or matter domination. So this is just a comparison of scenarios. This is a comparison of various inflationary scenarios. This comparing sorry, this is comparing the P goes to infinity. This is more or less the the quasi de Sitter case. And in this case, we're assuming there's a matter domination before radiation domination. So this piece goes K to the minus 7. But these are the on the other hand, if you have a slightly more different inflation from the quasi de Sitter inflation, that this type of the spectrum will be different. And this is by assuming I still have a quasi de Sitter inflation to begin with, but yet when the gravitational wave signal enter the horizon, whether it's radiation domination or whether it's a matter domination transition into a radiation domination. Okay, so these are different transition times. You see that they are different. Okay, so there's a quite distinct difference between both the shapes and the amplitude again. Okay, so I think that this is quite interesting because this kind of gravitational wave, this phase transition could happen at any point in general. Right, so in particular, it can happen after the CMB mode being generated during the inflation, and they can re-enter the horizon before, for example, Big Bang nuclear synthesis, and so on. So this time in the history of the universe is usually known as the cosmic dark ages. Okay, just because we don't have any useful probe into this era, and the most simplest assumption is that the single field inflation keeps going and reheat back into a radiation domination. But that's just very simple. That's the simplest model, right? So it's very easy to imagine there's a matter domination case before the radiation domination, for example. It's very easy. It's easy to imagine that the inflation, inflation the story is not that simple, right? It can have a different stages and the modifications of a simple quasi de Sitter. So, but normally from CMB, from a large scale structure, we don't have enough probes into this area. But this gives you, if there is a phase transition during the inflation, I think this gives you an interesting probe into the cosmic dark ages. Okay, so I'm coming to my conclusion. So again, I think cosmological observations can reveal this new dynamics in this inflationary era. It can be a very good stage for new dynamics to happen. So I talk about two things. One is the production of new particles with the mass on the edge can lead to distinct oscillatory signals. Right. So contrary to at least to my intuition, that the non-derivative coupling does not actually lead to non-derivative tree-level process interactions, does not actually lead to large signals of this kind, because they induce a large back reaction to the particle to the mass of the particle you want to produce. And on the other hand, well-motivated derivative couplings and loop process actually leads to observable signal. Okay. And I present you a set of result in this class. And on the other hand, also I think another very interesting direction is that there is this large excursion of Inflaton field. And if we imagine anything that's coupled to the Inflaton, and this is can generate very interesting dynamics in those spectator sectors. So in this case, here I consider the possibility of this triggering a first order phase transition that leads to gravitational waves, and I show that it could be a very interesting for the cosmic dark ages. Okay, thank you.
Questions?
Can you go to the gravitational wave, the slide with the different scenario, the signal?
This one?
Oh yeah, this one. How well you can separate the different scenario from the measurement? I mean, can you distinguish a different scenario from measurement?
Yeah, so I think it's a I don't know, I have to say. So this is I can only say that the signal of this size it is within the reach of some of the future future experiments.
Okay.
Right. So for example, you can look at this, right? These are some of these signals. Right. These are some future experiments. So it's not out of the signal at the omega gravitational wave on the order of 10 to the 13, maybe even further, and it's not really out of the question. It's still really a future prospect, but it's not out of the question. We can see some of these signals. Also, once you see this signal, then it depends on the precision that you can measure them to see whether you can distinguish them or not. So if you see these oscillations, let me just emphasize again. If you see these oscillations first, then it's just it tells you that there is instantaneous source of gravitational wave during the inflation. That's what it's telling you. Okay.
Okay.
And I think a plausible instantaneous source is this first order phase transition. And maybe there are other sources, but any instantaneous source of gravitational wave is going to give you this solution. Then, in order to distinguish those scenarios, you need to measure the slope of these signals. Okay. So that's it really depends on how big the signal or what's the
okay.
Yeah.
Thank you.
But so for the second calculation, you were always assuming that they were non-derivative couplings. Is that right?
So which calculation? This one?
The phase transition,
Wave.
gravitational
Oh.
wave.
Yeah, this is this kind of coupling. It's basically like you know, if you want phi square m square, this for example. Yeah, so these two are separate, motivated by separate things. This is just the fact that the inflaton can be one of the moduli that have a suppressed coupling to some spectator field.
Yeah, which means in the second case, in the gravitational wave, the non-terrestrial coupling will lead to large signal, right? This is conclusion.
Well, it's this non-derivative coupling. You can actually imagine that the number can change by order 1.
Oh, okay, okay.
Right. So then you can have a order 1 change in the Lagrangian of the spectator field.
Okay, true. Because
Okay,
in the
so imagine that you write a scalar field, a scalar Lagrangian for spectator scalar field, and then imagine I give you a knob, allow you to change any parameters by order 1.
Okay.
Okay, obviously many things that can happen. So I explore the case where this can trigger first order phase transition.
How much does that break?
But in general, I think there are many more possibilities. You can imagine if I can give you a sector that you can change order of magnitude by by order 1.
How much does that break the shift symmetry of the inflaton?
It actually does not. It's not actually a strong breaking, right? This is a big change for the spectator field. On the other hand, it's coupling to the inflaton. Now you're not treating this as a background field. This is as an actual field. It's still a small coupling. It's still suppressed by n.
Which means m square is much larger.
Yeah. So if you wanted to like calculate, for example, back reactions to the inflaton field, I don't think it's going to be a lot. So just imagine this capital M is m plot.
Okay, well, let's thank LianTao again.
Right, thank you.